And so it's an application of bioretention there at a residence. One thing I would recommend is that you don't mess with your utilities. They seem to have caved their utilities in putting this in, so definitely want to avoid that as much as possible. So this is our typical fat street, if you will. Typical 20, 22, 24, maybe even more foot wide street. This is my boss, Bill Hunt. I'm gonna call out names here, and this is Neil Weinstein from the LID Center up in Baltimore, Maryland. And they're having a good time laying out across this fat street. This happens to be in Seattle. And then this is their C Street, their street edge alternative street that I think maybe a lot of you have seen. There's Neil and Bill, and I think they're both about 7 feet when they stretch out, so it's a 14-foot wide street. And they have planter bioretention cells along both sides of the street where they're collecting runoff and infiltrating it. We'll say this wasn't the cheapest project in the world. They did $1.5 blocks. Does anyone want to venture a guess as to what it costs? This will be less painful if someone throws out a number. $500,000. $1.4 million. I would say that is not, it's definitely not going to happen in North Carolina. I don't know whether y'all want to spend that kind of money here. It wouldn't fly in North Carolina, I can tell you that. All right, again, in Kapiti Coast, New Zealand, this is an example of what you might do in a roundabout. Obviously different plants from what we have here in Georgia or in North Carolina, but very similar idea. Depressed area in the center of the roundabout, or the cul-de-sac, I should say. And instead of having the cul-de-sac drain to the outside, we've drained it here to the inside. So we're changing our grades in our engineering plans. Filtera type systems, there's a lot of these out on the market now. Contech has one. A number of different companies make these where you've got a very, very specialized media with like 100 inch per hour infiltration rate. You're able to put a lot of water through these things. We are studying these right now in Fayetteville, North Carolina for their performance. So we'll have some data in the next year. Another ready-made example from Auckland, New Zealand. So you can see kind of an inlet here with a little bit of a pre-treatment area to get the trash and sediment out. And then your filtration side there in the bottom of that picture. NCDOT, our DOT does a really good job with stormwater management. They've got, I think, over 150 bioretention cells installed at this point. So you can see a couple here. They look pretty good. Very, very large systems. Typically, our DOT has very large systems that they've installed. This is probably the most famous one. Prince George's County, Maryland. This is, I think, 1998. This is the first one that was installed ever in a depressed in a parking lot island there. Lewisburg, North Carolina, this is a research project. I'll show you all some data on this later. This is essentially in a turnaround in a park. You can see the bioretention cell there at full ponding. You can see in this case we're using a filter strip, a grass filter strip with a gravel verge as our pre-treatment for this particular system. Queensland, Australia, this happens to be a bus terminal. So lots and lots of parking and rooftop that are being conveyed to this long linear bioretention cell. This is a school. I think this is up in Maryland, actually. You can see kind of this area here. This will be retrofitted in the next picture. You can see kind of the aesthetic value that these practices bring when they are maintained. So quite a lot better than the parking lot that was there before. The Marine Corps Air Station in North Carolina. This is the Officers Club. They put in a very small planter box bioretention cell right up against the building itself. You can see they have an elevated outlet structure here just to provide 6 inches of ponding in that small planter bed. So you can fit these in very, very ultra-urban applications where there's not a lot of space to treat stormwater management. That's just taking one downspout. So it's this one downspout right here that's being treated. Another example of ultra-urban application, this is in downtown Alexandria, Virginia, where they've got internal downspouts that are being routed to this bioretention planter here. 100% impervious cover in this particular watershed. And then high dollar landscapes, this is Seattle. They've got, in this case, tiered bioretention cells out in front of a commercial building. So again, very high cost there for installation. And then we've got a relatively low cost application. This is in Charlotte. I think some of you all might be familiar with this one. This is right outside the Hal Marshall building in downtown Charlotte. You can see downtown there in the background. And there it is about 6 months after construction. So some examples of what you can do and where you can use bioretention cells. You can use them in many different areas, residential, commercial, ultra urban. I hope I've convinced you of that. And most applications are either going to treat roof or parking lots. That's pretty much what you're limited to. All right, so how do these systems work? Typical schematic here, so you've got water coming in from your parking lot or your rooftop. That water then fills up the bowl. That bowl may be 9 or 12 inches or maybe a little bit deeper. You have vegetation on the surface. You have water then moving through a permeable fill media. And it should say almost always sandy. It's not really often. It's almost always sandy. And then the water moves down and either out through the sides or the bottom, which we call exfiltration, or drainage out through an underdrain, which is typically installed, as Corey said, unless you have very, very high infiltration rates in your underlying soils, basically coastal plain type applications. Drawdown of bioretention cells. You do need your bioretention cell to draw down, otherwise it will turn into a wetland, right? If you have extended periods of water, your plants will die off and it won't function as a bioretention cell. So right after the storm event, the water will have filled all of the media as well as the bowl. What we recommend in North Carolina is having an infiltration rate such that that bowl draws down in a 12-hour period. So you should see no water on the surface after 12 hours after the end of rainfall. And then we want the water table to draw down an additional 2 feet below the bottom of the bowl. So basically 2 feet of media would be drained after 48 hours. So that's our requirements in North Carolina. I think that dovetails pretty well with y'all's here. Pretty close to what you guys have to meet as well. So here's an example. This is back to the Hal Marshall building in Charlotte. Right after the storm event there, you can see the bowl is filled up. 4 hours later, we're starting to get some drainage. And then 14 hours later, you can see the mulch is moist, but there's no surface ponding. So that's what you want to see is that surface bowl completely drained within 12 hours. That's going to give you the best long-term performance. Design objectives for bioretention for water quality and water quantity. You can completely control the 1-year storm depending on what you do, and maybe the 2-year storm depending on how you design these systems, and I'll talk a little bit more about that later. You can obviously partially control the larger storms, but you're not going to get anywhere near complete control of the 10, 25, or 100 year. Water quality control, we're typically designing in North Carolina for the 1-inch storm in the Piedmont and the mountains. We do have a slightly larger 1.5-inch storm event that's used for design in the coastal plain, and that's just simply because they get more rainfall. They get roughly 20% more rainfall in Wilmington, our coastal city, than we do in Raleigh. Then there's also various jurisdictions that require groundwater recharge, and so these systems obviously will provide you benefits in groundwater recharge, as I'll show you. Seasonally high water table, is that a problem with bioretention? Yes, it is, right? We don't want to trade a surface water issue for a groundwater issue. So groundwater is arguably, I would say, harder to treat than water that you have at the surface. So areas where seasonally high water tables are near the surface, namely coastal areas, floodplains, wetland areas, those are going to be areas you want to avoid. What we recommend is no water table within 2 feet. This says 1 to 2 feet, but I know that engineers cheat, and so 2 feet of the bottom of your cut. And I think it's 2 feet here as well. So the reason for that, or what that means, is if you have a 1 foot ponding depth, a 1 foot bowl, and if you have 3 feet of media, and let's say roughly a foot of aggregate in your drainage layer, your water table now has to be 6 or 7 feet below grade. So you really do have to have some depth to your water table to make these systems work, unless you have a shallower media depth than the typical 3 feet. And the reason for this is just to have some native soil underneath the bioretention area to filter out any additional pollutants that have made it through your media and to the bottom of the cell. All right, pollutant removal mechanisms. The reason why bioretention works so well is I think it's got the most pollutant removal mechanisms out of any BMP, any green infrastructure BMP that's out there. So sedimentation, basically the water's coming in, it has velocity, so therefore it's picked up particles and trash, right? And you're putting in a basin, so the velocity is pretty much near zero. So your trash is going to drop out, your suspended sediment, a lot of that is going to drop out. And because a lot of phosphorus is attached to sediment, you're going to get at a lot of the phosphorus that's in the water as well. Microbial processes, denitrification, which we can force with the internal water storage zone that Corey plugged earlier, and I'm going to talk, I think, ad nauseum about. we can get a lot of denitrification and take our nitrogen to N2 gas, which is 76% of our atmosphere, right? So we're breathing it constantly. Harmless. Chemical processes and filtration are going to get at our metals and phosphorus. Basically, they're going to adsorb to either organic matter, which is basically chemically bind to organic matter, or clay and silt particles. And then exposure to sunlight. So the reason we want these practices to dry out is to kill off the pathogenic bacteria and to break down the oil and grease that is coming in off of our watershed. And then obviously infiltration is going to take care of a part of our pollutant load that's coming to our practice. So in terms of hydrologic control, these systems really are going to provide temporary surface storage and then media filtration, so vertical flow through a porous media. They're especially effective for small storms, so those storms below your 1-inch design storm here in Atlanta. So those frequently occurring storms. They're not going to get at, substantially reducing Hurricane Floyd or Hurricane Fran's peak flow, for instance. Okay, so some common design questions. Are there any Tennessee alumni in here? Because that guy kind of looks like one, right? I like that. It's like the same burnt orange color as Tennessee. So this is one of our old grad students. Anyway, ponding depths. What ponding depth do we want to use for bioretention? This is obviously a big question because the deeper the ponding depth, the smaller the surface area of the practice gets, right? So the cheaper it is to build, hypothetically. So first I will show you a couple of examples of ponding, question mark, as in I'm not sure it's occurring. So there's a lot of this that happens, over mulching, right, where people get really, really mulch happy and they just dump in mulch and you don't have any ponding area in that cell. There's a lot of this that also occurs where the contractor thinks he'll do you a favor and put a grate in so that you get drainage. And so I would argue there's probably not much ponding in that cell. And same thing here, right? The gutter is coming right to the drain and there's no way for the water to get into the bioretention cell. So that's something on the construction oversight end to watch, because often contractors will, again, think they're doing you a favor and they're really not. So maximum ponding depths, again, this is an NCDOT bioretention cell. You can see the overflow structure here. Your ponding depth, of course, is going to be set by the invert elevation of this grate, right? So that's really critical to get that elevation correct, and it's something that should definitely be checked post-construction by whoever is doing the construction oversight. So here's an example. This happens to be my leg, and it's about mid-ankle on me, so this is roughly 12 inches of ponding, which is our typical ponding depth in North Carolina. So our requirements are somewhere between 9 and 12 inches of ponding, which of course means that everybody is going to go with this number, right? Because it results in a smaller practice, of course. I will say there's some jurisdictions in North Carolina that allow you to do an 18-inch ponding depth, and that does appear in sort of qualitatively anyway. We don't have any data on it yet, but it does appear to work fairly well. What they let you do is they still make you capture the 1-inch water quality volume in the first 12 inches, but then they give you an additional 6 inches of ponding that's simply there for peak flow mitigation. And so you basically have an orifice set at 12 inches above the top of the mulch, and what that does is it gives you an additional 6 inches just to mitigate perhaps the 1 or the 2 year storm, which you may or may not be able to get to with only 12 inches of ponding. So that is out there and has been done, and our DOT often pushes the envelope some because they don't have to meet the standard specs that our DENR, our Department of Environment and Natural Resources, puts out, so they can kind of play with some design variables. And this is an example of the bottom of a grassed bioretention cell. This happens to be in an interchange on I-440 in Raleigh. And you can see this has a 3-foot ponding depth on it. So really, we're getting now towards a dry basin or a wet basin at that point where we've got a lot of ponding. And you can see kind of the grass health. What would you say that is? Not very good, right? So we need a bio component to this. It can't just be retention and filtration. Otherwise, the practice is not going to function as well for water quality treatment. So this is not something, 36 inches is not something I would recommend. I think that's gone a little bit too far, in my opinion anyhow. Okay, so This bowl depth is particularly important because, as Corey mentioned in his intro, it does determine the surface area of the bioretention cell, and therefore that's obviously a key component of the cost. So your design calculations are a little bit different, but ours just gives you credit for the bowl storage. So ours is literally just a volume of water coming in off the watershed over the ponding depth in order to calculate the surface area. So it's a very simple calculation. This is, of course, conservative because we're not giving any credit for the void storage in the aggregate or in the soil. So we're actually getting more treatment here than sort of what's being credited. However, I would argue that a lot of these cells there's installation issues that occur, and so I think having a bit of conservatism here is not necessarily a bad thing. Our engineers in the state might argue otherwise. I'm looking at one right now, and he's laughing, so I think he would agree. This surface area doesn't include the pretreatment, and we'll talk about pretreatment in just a little bit. So one question that you'll get, the typical bioretention cell, like what we have outside, I think maybe it's a little bit more of a bioswale, but what's out back here is a tree, shrub, mulch type system, right? But one question that we got early on in North Carolina is, can these systems be sodded? Can they be grassed? And the answer is yes. We have done research on them, and I'll show you a little bit of data. Some of the concerns that are out there is, with turf grass, often your rooting depth is very shallow, say 3 to 8, 12 inches deep, if you're lucky. And so over time, are you going to really have enough organic matter in that soil to do some of the denitrification type activities, some of the microbial processes that we need in the soil to have good performance? And then the other thing is, because you don't have a deep rooting depth, will these systems compact more quickly? In other words, will the soil compact because you don't have roots that are going 2-3 feet deep into the soil and creating macropores for vertical flow? So here's an example of a grass bioretention cell. There's a number of them in North Carolina. I would say, if I had to put a number on it, somewhere between 10 and 25% of our bioretention cells are grassed. So this is at Graham High School. This is one that one of my predecessors designed, and you can't really see it. There's one right here, and there's one right here, and Graham High School happens to be the Red Devils. And so these were, if you look at this from a plan view, these are devil eyes, which is kind of cool. We engineers do have some creativity. I like to point that out when I can. But you can see the underdrain cleanouts here, the inlet is right here, and there's an outlet which is just a broad-crested weir right here. So it's a very simple system. It does have media underlying that grass, of course.
So those mounds are purely decorative, don't have a functional?
The mounds are there, yeah. This middle mound really is decorative, yes. Yep. And then the berms around the outside, of course, are to hold the water. Yep.
It has flow path too, though.
It does have a little bit of flow path, yeah. Yeah. And it looks a little bit better, I would say, than just a rectangle. So,
what's your minimum top width on a berm? Especially when you're looking at 6 to 12 inches of pond.
Yeah, I mean, this one is probably 3 feet wide and it's just a triangle.
On the outer.
On the outer.
The impoundment.
I don't know if there's actually a standard for it. My gut would be I would want like 2 feet probably at a minimum, just flat, yeah, and then 3 to 1 side slopes coming down to the ponding. Yep.
Do you know how they're mowing it?
How they're mowing it?
It looks like you have to have a small mower.
It is a small mower. That's correct. Yeah, you're not going to have a big batwing mower out there mowing that. That is correct. Yep. Here's an example of one on NC State's campus. This happens to be pretty near my building where I'm housed. You can see the ponding depth here. It's just a simple retrofit of an existing catch basin. They dug out around it, put in specialized media, and called it a grass bioretention cell. What you will get is some of these. I like to call these "Hey y'all, watch this" moments, right? Typically, it involves a large truck and a few guys, and they did donuts in this particular grass bioretention cell. They actually did us a favor, though. One thing you have to be careful with grass bioretention is where your sod is grown, right? Because you have a really nice porous media underneath it. And if you grow it on Central Georgia red clay, what do you do when you cut sod? You have, let's say, a quarter, half inch of soil that comes off of that sod cutter, right? And so you've just stuck a really nice clogging layer on top of really expensive media. So this guy actually broke up some of the clogging that was occurring because we got this particular sod from the Piedmont of North Carolina where we have clay soils as well. So what I would recommend is if you're going to put in grass bioretention, get your sod from the coastal plain or spec washed sod, which is something that the golf course industry uses for specifically for greens, for the greens on a golf course. Typically has next to no soil on the sod, so it's like bare root sod pretty much, and you can get that commercially available. It is more expensive, but it will prevent clogging at the surface. All right, how much fill media is needed is another big question that's out there, because you're going to spend $25 to $30 a yard in North Carolina on bioretention media, so it is very, very costly. So the shallower you can make your media, the cheaper will be your cell. So basically, what is that depth there, that media depth? It's predicated upon 3 factors. It's the vegetation health, right? You have to be able to grow something in it. The hydrologic goals, so how much water do you want to store and infiltrate? And then your water quality needs. So what pollutants of concern do you have in your particular watershed? Okay, so for soil depth, the minimum recommendations that we have, typically with turf grass, you can get away with a 2-foot depth. That's actually probably more than you need. And then with shrubs and trees, we say a 3-foot minimum media depth is required, with 3.5 to 4 feet being optimum, but you never really see these going in because they're more costly, of course. So some thoughts, deeper cells do provide more moisture reserves for trees and shrubs, and they can tap into those during droughts or extended dry periods. And then obviously deeper cells provide more runoff volume because you have more porosity in that soil media than you do in the underlying soil typically. So some justifications for different minimum media depths based on pollutant. There's been a lot of research on bioretention. I'm sure some of y'all are very familiar with it. And so these are the minimum recommendations that we put out based on different studies that have been done. TSS, metals, oil and grease, things that are captured right in